So the next talk is by Ashati Weeraratna from Hopkins University, where she's a distinguished Bloomberg professor. And Daniela Cerezo in my lab warned me already about the originality of the titles of Ashati's talks. And I think this keeps the level, or at least the original, is the Age Against the Machine. So thank you, Ashani.
All right. Well, thank you so much for having me join. This has been actually just an amazing morning listening to everyone. I'm sorry I was not able to be here yesterday because I had a board meeting all day. But I'm delighted to talk to you about some of our most recent work. Much of what I'll talk to you about is unpublished. So please don't post anything. I don't know if any of us are still on Twitter. I am not. So if you do post, I won't see it, but please don't post. So we have been very interested in trying to understand how aging drives tumor progression, as I think everyone at this conference is interested in. And that is because, as you will have seen the stats, for every 100 people diagnosed with cancer, almost 90% are over the age of 50. And, this aging has multiple aspects. There's an increase with incidence and mortality with age. There are changes in the way tumors respond to therapy with age. And something that we've become increasingly interested in lately is how therapy itself can accelerate aging. I won't talk about that today, but it is becoming a very interesting aspect of this whole aging paradigm. We've been very interested in how the tumor microenvironment ages and how that impacts the tumor. And so no tumor is an island, and it lives in this milieu of cells. You've heard about adipocytes from Amaya, fibroblasts from Francis, and I will talk a little more about fibroblasts as well. But obviously, there's a whole host of other cells, including endothelial cells, and immune cells, and we'll discuss some of those as well. We've become very interested in aging fibroblasts. They really drive multiple aspects of tumor progression. And they do this both through secretion of molecules that can affect the signaling within tumor cells, but also through changes in the extracellular matrix and the biophysical matrices, as you heard from a little earlier today. And these changes affect not just the tumor cells, they also affect the endothelial cells and the immune cells, and all of these changes can come together to drive tumor progression. So over the years, we've shown that these aging fibroblasts affect multiple different aspects of tumor progression, from the resistance of tumors to therapy, angiogenesis, metabolism, changes in the immune microenvironment, emergence from dormancy, as well as changes in metastasis due to changes in the biophysical matrix. And so something we had seen is that tumors metastasize more effectively in animals that are aged 12 to 18 months. I will say that, there's a lot of emerging data now that in very old animals that are 24 to 36 months old, metastasis is actually decreased. We see that as well. We think that part of it is due to the fact that these animals also have a whole host of other issues. But for the purpose of my talk, when I talk about young and aged, I'm talking about 8 weeks for young and 12 to 18 months old for aged. So Mitch Fain in my lab, who's now an assistant professor at Fox Chase in Philadelphia, he wanted to know, did tumors leave the skin at the same rates in young and aged animals, or did they leave at different rates or grow out differently at the distal sites? And so what he did was an experiment where he implanted melanoma cells in the skin of young and aged mice. He gave them a few weeks to disseminate, and then he examined the lungs. And when he does that, he sees that there are small single colonies that happen that metastasize to the lungs from the skin in both the young and aged mice. But if he waits just a couple of weeks more, you can see that those colonies grow out very rapidly in the aged mice, but not so much in the young mice. And when he looked at what the culprits might be for this, he found that it was aged lung fibroblasts that really secrete a lot of factors that drive the increased proliferation of these cells in the lung. Mitch did some proteomics analysis, and what he found was that in the aged skin, we see that non-canonical Wnt signaling we see that in the aged lung, in the aged dermal fibroblasts drive non-canonical Wnt signaling, such as SFRP2, Wnt5A, etc. And in the aged lung, there is a drive of canonical Wnt signaling. And we know that in melanoma, non-canonical Wnt signaling promotes a slow cycling, but highly invasive phenotype, and canonical Wnt signaling promotes a very proliferative phenotype. And when Mitch looked at his secretome results, he found that there was a distinct difference in the types of Wnt signaling modulators, even from the same family. So we have SFRP2 and SFRP1, and SFRP2 we know drives this highly invasive but slow growing phenotype. And SFRP1, Mitch showed us, decreases non-canonical Wnt signaling, drives a more proliferative phenotype. And if he injects his mice with tumors in the skin, allows them that 3 weeks for initial dissemination, and then treats them with an antibody against SFRP1, he's able to revert this outgrowth of metastases. So whereas the metastases grow out very rapidly in the aged lung, in the absence of SFRP1, they no longer can do this. So this is just to show you that tumors metastasize faster in the aged lung, and that's due not necessarily to a rate of dissemination, but actually to the outgrowth of these tumors in the aged lung. And the fact that these tumors were outgrowing rapidly in the aged lung made us wonder whether the immune microenvironment was also changed. Was it just that the fibroblasts were secreting these molecules that promoted a highly proliferative phenotype, or was it a combination of that and changes in the immune microenvironment? We wanted to know, did these tumor cells get to the lungs and then have effects on the fibroblasts there, eventually making them more cancer associated, if you will? Or were the fibroblasts the ones that aged and drove the tumor? And as you can imagine, it's not really a chicken or an egg, but instead a combination of both of these things. That has been very exciting. So it's telling us that, this outgrowth of dormancy that we're seeing in the age microenvironment is a mixture of the fact that the fibroblasts are secreting molecules that are driving the proliferation of tumor cells, but they're also creating an immune microenvironment that is suppressive, that is an immune suppressed microenvironment, which allows the tumors to grow out and grow out rapidly as well. I will switch to another story in the lab that has just been published that I'd like to share with you. And, this actually came out of many of the lab discussions that we have. For any of you who know me, you know how important it is to me that we have a diverse and equitable space in science. Come January in this country, I'm not sure how much more I can talk about this publicly, so I'm going to take my chance now while I can. This is Kimberly Crenshaw. She's one of my favorite people. She talks about intersectional equality. So, what are the different things that make you experience the world in a certain way and the way the world experiences you? So what does it mean to be gay and Black or Hispanic and a woman? And how do all of those inequalities shape who you are and shape the way the world sees you? So as I mentioned, we talk about this stuff all the time in my lab. And in a discussion several years ago, Yash Chabar, who was then a research associate with me, who's now an assistant professor in his own right as well, said, we talk a lot about intersectionality in terms of diversity, but it would be also interesting to talk about intersectionality in terms of science, because if you look at the rates of melanoma in men and women, they are very different. And in fact, we see that men die more, the mortality rate is increased in men as compared to women, even though mortality rates increase overall in aging. And so Yash decided to explore this. And I put this slide up here just to say we know aging is incredibly complicated. The sex differences are incredibly complicated. There's hormones, there's sex chromosomes. The immunology is very different. But we wanted to kind of break it back down to its basic elements. And so what Yash did, and I'll go very quickly through the in vitro data so I can give you the in vivo data, and then I'll be out of time, I'm sure. But what Yash did was to take male and female fibroblasts, young and aged, and look at all of the differences between them. And I'm just showing you some snapshots of a few of them. He found that as aging increased, there were changes in proliferation and changes in senescence. And the changes in senescence were quite interesting because in the young female fibroblasts, there was actually way more senescence than in the aged male fibroblasts. And it turns out that that senescence in the young female fibroblast was not associated with a senescence-associated secretory phenotype, and instead allowed those cells to stop, think about the DNA damage they were undergoing, and repair it. And so over time, those cells became uniquely fitter, if you will. And so I think this is a really important point because we've heard a lot about senescence, and I'm here to say that senescence is a continuum. We see senescence in embryonic development, and confusing senescence and aging is really something that drives me crazy when people talk about senescence as if it's aging a lot. And so I'd really like to make the point here that senescence is, a very complex phenomenon that we don't fully understand yet. But it should not be conflated with aging and is not necessarily a marker of aging. We see that there are changes in the metabolism in these fibroblasts. You can see that there are changes that happen with age in both age male and female, but tend to be more pronounced in the age male. And that's sort of a theme that we saw over and over again with these studies. So Yash decided to do a large experiment where he took young in age, male and female mice, and then he took male and female melanoma cells and he put them in the young and aged male and female mice. So it was a massive experiment, big crisscross, and I'll try to explain it as carefully as I can. So if he takes the male melanoma cells and he puts them in all of the different conditions, what he finds is quite consistently, those cells grow more slowly in the aged male mice. In aged female mice, if we take female melanoma cells, we see the same thing again, which is where the cells grow more slowly in the aged male mice than in any other condition. In both the male and female melanoma cells, the cells metastasize more in the aged in general, but way more in the aged male mice than the aged female mice. If we look at markers of DNA damage in these tumors, again, regardless of the sex of the melanoma cells, there is more DNA damage in tumors in aged male mice than in any other condition. So melanomas are largely driven by the BRAF oncogene. This is actually less true in melanomas in older individuals, but regardless, our cells are BRAF mutant. And there are wonderful inhibitors to this pathway. I'm sure many of you have seen these images before, but this is a gentleman who presented with metastatic melanoma, was treated with a BRAF inhibitor, and then several weeks later, the tumors recurred. It turns out that older patients actually respond less well to BRAF inhibitors, even if they have the mutation. And one of the experiments we did several years ago that really blew my mind was that when we treat, that if we take melanoma cells that have the BRAF mutation, we put them in younger age mice, and then we treat them with the BRAF inhibitors, they consistently respond less well in the age mice. And that was surprising because we kind of thought you have one mutation, one drug, nothing else should matter. But of course, the microenvironment always matters. And so we see that the same holds true in Yash's experiments, but now he's added in the conditions of male and female. So what you're looking at here are spheroid assays. These are melanoma cells bathed in conditioned media from young in age, male or female fibroblasts. The more red you see, the more cells are dead. It's quantitated over here. The age male conditioned media increases increases the resistance of the melanoma cells. And it turns out this is also true in vivo, where if you look at the tumors in vivo, in the aged male microenvironment, they do not respond really to the BRAF MEK inhibitors. They slow down a little, but they keep going through it, unlike the young, which do respond and then eventually come back. But in the females, we saw something very interesting, which is that both aged and young females responded to the BRAF/MEK inhibitors, but it was in the aged females that they started to rebound much more quickly than in the young females. So Yash wanted to know what was driving this. He did a bunch of proteomics assays. He identified BMP2 as a potential driver of this difference that we were seeing. It's increased in aged male fibroblasts over any other condition. It's increased in tumors in aged males, in tumors in the aged male mice. And if he uses an endogenous inhibitor against this BRAF/MEK inhibitor, he can increase response to the BRAF/MEK inhibitors. And so this work has just been published. I've given you literally a very, very tiny snapshot of Yash's work, but I encourage you to read the paper if you can. He really has done an amazing job, and I'm so excited to see what he does with this work in his new lab. So just to summarize what he has shown, he's shown that female fibroblasts undergo an early senescence, but have a delayed senescence-associated secretory phenotype. Male fibroblasts undergo intrinsic aging programs. There's a lot underlying this that I haven't really spoken about, including changes in the epigenome. And the male fibroblasts also seem to create a tumor microenvironment that allows the tumor cells to increase their resistance to targeted therapy. We have multiple other projects ongoing in the lab, including looking at the aging of the primary immune landscape, as well as looking at how changes in the aging matrix affect the way immune cells are coming in and out of tumors. We are looking at UV light as a driver of premature aging, and that has been really fascinating as well. And we're looking at changes in distal sites, the lung and the brain microenvironments, including changes there in angiogenesis, as well as the secreted factors. Something very interesting that we're finding in the brain is that the phenotype switching of the Wnt signaling is actually driving the types of metastases that are forming, and that's been super exciting. And then we're also looking at ferroptosis and melanoma cells in an aged microenvironment. So I hope I don't think this is an audience I need to convince that aging is critical for everything from changes in the matrix to angiogenesis to metabolism and metastasis. It's so important that we take aging into account when we're designing preclinical studies, as well as designing clinical trials, obviously. So this is a slightly older picture of the lab. Yash and Dan have both now gone on to start their own lab. Laura has gone off to industry, and Megan and Edwin and Ani have all gone to medical school. So I do need to update this slide, but these are the amazing people who do all of the work. Incredible collaborators at Hopkins across the country, across the world. And I'll end hopefully on time with a picture of my favorite aging study, my daughter. And I'll stop there and I'll take any questions.
Thank you, Ashani. Nice experiment. The last one.
Thank you. My favorite.
So great timing. So we have time for a few questions. There's the first hand that is raised. Let me see whose hands it's because from Amaya. Amaya, go ahead.
Thank you, Ashi. That was a lovely talk. You mentioned that the MDSC phenotype in the aged lung suppresses the T cell activity better.
Mhm.
So how did you measure that? And do you find a difference between the aged T cell in the lung and the systemic T cells just natively?
Yeah, so how we did that was to isolate the myeloid-derived suppressor cells, culture them, and then present them to the T cells to check the suppressive activity, the proliferation of the T cells. So it's very standard MDSC functionality assay. Happy to send you those protocols. And then in terms of the systemic differences, so we have looked at the blood, the spleen, the lungs, and then the primary tumor. And there are differences in the spleen and the lung that show us that there's an increase in the myeloid-derived suppressor cells. For the CD8 cells, what we see is that so what we have looked at are the CD8 cells, the Tregs, and the MDSCs. And in young tumors, in the primary tumors, what we see is that there's no real difference between the amount of CD8 positive cells, but the ratio of the Tregs to the CD8 positive cells is actually higher in the tumors in the young mice. And we published a few years ago that that actually makes those mice respond less well to anti-PD-1. So in terms of the lungs, we see that there is a decrease in the CD8 cells. We have not done the CD8 to Treg ratios in the lungs yet. So, thanks.
Okay. This well, it's not a question. Someone is curious about who your collaborators in Oxford are.
So for
you couldn't see
yeah.
that.
So when we did our angiogenesis study, which I didn't present here, we collaborated with Mark Middleton and Andrea Johnson, I believe is her last name, to go through all of the patient data.
Okay, I'll do a question. Maybe we get some more questions from the audience. So, Ashani, I'm just curious. I'm very ignorant about all these things, but is senescence accelerated in the skin by any reason? Is there a male to female difference? And touching this, I guess you're doing additional studies that you didn't mention, but is this hormonal related or any other specific path that increases role? So this very interesting susceptibility of aged male mice to
Yeah.
to
So to answer your first question, there is an increase in senescence during aging in the skin. It's not huge. And what we're now seeing is that in our aged lung fibroblasts, so not the skin, but the lung, that senescence can be decreased in the presence of melanoma cells, right? So I just presented that. Overall, there is, I think as we age, we reach about 15% senescence in the skin, which I think is what you were asking. If that's, again, I'm very cautious about interpreting senescence as a driving factor of any of these phenotypes, because honestly, we're not seeing that.
Yeah, and I imagine being not from the senescence field or fibroblasts or cancer. I mean, what am I doing here? It's difficult to test things out because despite all those senolytics and so on and so forth, and there's phenotypic changes, but it genetically is very. Correct me if I'm wrong. There is difficult to trace and to modify senescence, right? Because it's so multifactorial, I imagine.
Yeah, and I think that we don't really fully, senescence, when I started working on all of this stuff, people said senescence was irreversible. We now know that's not true. It's not irreversible. You can add in nucleotides and, reverse it. You can change a condition and reverse it. So until we fully understand what senescence is beyond beta-gal, I don't think we can, effectively target it. And that's probably a super controversial opinion to express here. But
Exactly.
I honestly do feel that we need to understand it better than we do in order to properly target it.
Okay. And if I made sense, there's some questions that I want to capitalize just very quickly. The matrix, do you think it's a very influential factor? There was this paper by the Bloomberg lab talking about the influence of the stiffness and compliance of the skin. And I imagine that's very much linked with fibroblast senescence as well.
Yeah. So aging fibroblasts, not senescent, aging fibroblasts create in the skin a much stiffer matrix. It's a little counterintuitive because it's less collagen dense, but the collagen fibers are more bundled and they're stiffer.
Okay. So there's the three questions. I just saw them now. Sorry, I didn't mean to capitalize. So Guillaume Beltier is asking, does melanoma cell lines not BRAF mutated react as the BRAF mutated ones?
Yeah, so that's a great question. We have looked at a couple of non-BRAF mutated. We do think it's going to be a dividing factor. When we look at NRAS mutated lines, they behave a little differently. And I'll have a more fleshed out answer for you, hopefully in about 6 months from now. These experiments take a long time in aging mice, as you can imagine.
So Jackie Guts is asking, hi Ashi, any idea on what reduces metastasis in the very, very, very old mice?
Hi, Jackie. That's a great question. I think it's going to be a mix of several different things. So I think one of them is going to be the fact that the skin of the age mice has become, as you know, with older individuals, there's degradation of the collagen and elastin over time. And early studies in metastasis showed that you have sort of this bell curve of metastasis with stiffness, right? Where in a very stiff matrix, things don't metastasize, in a very soft matrix, things don't metastasize, and there's sort of this sweet spot in between. So I think that might be some of the initial steps of metastasis. But even tail vein injections are showing that there are fewer metastases in the very, very old mice. Now, those mice, remember, have pituitary adenomas. A lot of them have lymphomas. And so I think there's so much going on with those old mice that they might just not have an environment that's fit enough for the metastases to take hold. And you do see that in the bell curves epidemiologically as well, where patients, it kind of increases and then it tails off after a little bit in the 75 to 80-year-old range.
Okay, thank you. The last question from Karin Sengal Mitch. Sorry for slaughtering your last name. Very interesting data. Is immunotherapy showing the same sex age differences as targeted therapy?
Yeah, Yash is doing those experiments right now in his lab. So hopefully he will have an answer for you very soon.
Wonderful. Thanks so much,
Thank you.
Ashani. We need to move on to the next speaker. Thank you.